So first, Joanna Linders from the SMHI will present the in-situ products. So Joanna, can you open your microphone, please?
My name is Johanna Linders, and I am the manager for the Baltic region part of the Copernicus Marine Service in-situ team. And I'm working as a physical oceanographer at the Swedish Meteorological and Hydrological Institute, SMHI, in Gothenburg, Sweden. And I would like to start with a quote from Carl Wunsch. Without sufficient observations, useful prediction will likely never be possible. Models will evolve and improve, but without data will be untestable, and observations not taken today are lost forever. So I have four main objectives I would like to present today. It's the in-situ data, the in-situ TAC, in-situ TAC products, and the in-situ TAC improvements. And for you that are not familiar with the term TAC, it stands for Thematic Assembly Center, and it's really widely used in Siemens. So we start with the in-situ data, and in-situ data is certainly a multi-platform approach. Today there are several ways to measure the ocean. We have vessels, which takes vertical profiles, also have mounted ADCPs on them for measuring currents. We have gliders, moorings, Argo floats, sail drones. We have HF radars and drifters to see, for example, currents. And we have Mariographs for the sea level. There are plenty of platforms available, even more. So we go to in-situ TAC. Our main objectives are to collect multi-source and multi-platform heterogeneous data and to perform consistent quality control and distribute it in a common format, NetCDF, and in near real time within 24 hours to the Siemens Marine Forecasting Centers, the MFCs, for assimilation into their numerical ocean models. And the second one is to supply the MFCs and downstream users with reprocessed 25 to 50-year products in delayed mode. In addition to the near real-time products, these delayed mode products are useful for model validation or assimilation in the ocean reanalysis and the climate studies. A general description of in-situ TAC is that we have been a fully operational service since April 2015. We have unique data access to all the available data. It's via the Siemens catalog, and you need to register it. We have an open and free data policy and a strong collaboration with the EuroGoose, CDataNet, and EMODnet. We have 7 components. It's the global and the 6 regions, the Arctic, Baltic, Midwest Shelf, Iberian, Biscay, and Irish Seas, the Mediterranean, and the Black Sea. All of the regions have the same data format, and you can find it more specified in our in-situ format manual. It's 1.4 at the moment. And we have the same FTP structure in all the regions. We have a homogenization of variable names, units, and attributes to simplify the use of the observations. We have the same real-time quality controls and quality flagging convention. And there are 2 product families for the in-situ TAC. We have both the reprocessed products and the NRT, the near real-time products. So here's an overview for the data flow from a provider, operator, to the end user. So we acquire the data, and it's not homogeneous, from different international organizations or providers, mostly through our ROSES, the regional oceanographic operational services. And we have this real-time quality control, and then we have a homogenization for the NetCDF files and synchronization with other PUs, because sometimes we have shared providers. And we distribute our near real-time products to the central destination unit. For the delayed mode rep product, we have a validation of the product, we visually check the data, and we have this scientific assessment, and then we distribute a rep product. For both those products, we also have these cross-cutting activities that will benefit them with management and documentation, product quality, system evolution, the Ocean Strait report, and of course the website. If you look at numbers, we have almost 7,000 platforms active for the real time, and we have 37 platforms integrated, and all this data is coming from more than 300 providers. Almost. So the in-situ TAC products, we have mentioned them, and here they are. They are the rep product and the near real-time product, and there are differences. For the rep product, we have an update every 6 months, but for the near real-time, we can update every hour up till within 24 hours after the measurement. And the scope for the rep product is global, but for the near real-time, it's both global and regional. The quality mode will be delayed for the rep product, but for the near real-time, we will have delayed mode plus the real-time. That means that when delayed mode data is not available, we will have the real-time data instead. For the topic is for the rep, we have one topic, and it can be waves or biochemical or time salinity. But for the near real-time, we have one or more topics. And for the names, I will come back to the name convention, but it looks like something like this. You have the in-situ global wave, and MI stands for multi-year. And for the near real-time, we have example for the file name, something like the in-situ and BAL, and MYNRT, that stands for multi-year near real-time. And in the rep product, we have biochemical data, we have currents, and we have the HF radar since April 2019. And we have waves, and wave spectra will be available in December 2020 for the rep product. For the near real time instead, we have like temperature and salinity, we have the currents, and we have the waves. Already in March 2020 now then for the wave spectra. So there will be some new concepts for those products, and for the rep product, we will replace the regional rep products with only global rep products instead, and then we will use this acronym mentioned before, MY, which stands for multi-year. And for the NRT products, we will have both regional and global products. And this product, as I said, will constantly be updated with the best version of the available data in terms of quality and time coverage. So in other words, it is the combination of adding near real-time data when there is no reprocessed delayed mode data available. And this near real-time product will have the new acronym MYNRT, which stands for multi-year near real-time. To explain it easier, this near real-time product is simply the best if you listen to Tina Turner. Well, the access and structure of our files. We have NetCDF files that are accessed from marinecopernicus.eu, but in the end, it's only FTP access that you need, but you need to register, as you heard before. We also have index files to smooth the navigation and search for certain stations or areas that you need. And the files are organized based on 3 periods. We have the latest, which is the last 30 days of data. We have monthly, which is the last 5 years of data, and then history, and that's since ever. That's the entire data set. So the folders are structured in these periods. You can see that for the latest, we have 1 file per day in platform. In the monthly folder, you can find 1 file per month on platform. And for the history, then we just have one file per platform. And you also have those index files. And it may look like a wall of text, and it is, but it's certainly also a useful wall of text. I don't think we should look so much in detail here, but you should know that in these index files, you can use machine to machine to actually easily find out which files you are wanting to download or search for certain stations. So you both have this index file for the latest observations, and we have also an index file for the different platforms. The file naming is based on diagrams, and in the beginning, well, you need always to come back to this to look at it more closely, but I can just go through it and say that we have a diagram for the region that will start the file name, and then you can look at the file type, which can be, for example, time series or profile, and then you look at data type, if it's a CTD profile or if it's a ferry box, for example, and then you can look at the code, which is actually platform code, the station name, for example. So this will build up the file name. We have a new format manual, and the most important changes we can mention is that we have an agreement in use of global attributes for the NetCDF files, and all global attributes are mandatory. Some of them accept an empty string. We have coordinate variables that set may be non-monotonic. We have a position dimension that may be 1 for fixed platforms. And we will have no full value attribute for time latitude and longitude. We have an agreement on data mode management for the global, variable, and value levels. And new here is the HF radar chapter and the wave spectra chapter, where we have conventions for both. And the names are also going to change up and coming for December 2020. I think it's not really decided yet, but it will change from something like in-situ BIO NRT observations and this number to in-situ BIO, and then you'll have a sum of the parameters of variables that you can find, like physical, biochemical, and wave. 3D is because we have both position and time, so we have a three-dimensional product. And the MYNRT is this multi-year near real-time acronym that we use. And it will be the same for the data sets as well. But this is up and coming, but now you have just seen it. So the in-situ tech improvements here. So we have a website, the marineinsitu.eu, and here you can easily read how to submit data for the in-situ tech if you want to provide observations. You can also read how you can easily access the data on the CMM site. And we have a dashboard, for example. You can also look at the documents here, and you can find the NetCDF formal manual that we mentioned. You can also find parameters list and the quality control procedures. At the web page, you can look at the KPIs, key performance indicators, and that can be interesting. You can see the number of platforms that are active in different regions. You can look at the data quality that is also provided from the different regions. The number of data providers, for example, and data files. So this is metadata about observational data. And you can look at the dashboard if you would like to visually check what kind of different stations there are in your area. And you can also access the data. You will be redirected, of course, to the CMM's site where you can download the data. Here you can visually look at geographically and find your station. So the added values we can say for the in-situ tech is that, well, we gather the data and it's not homogeneous in any way in the beginning. And then we have this basic service for the format, we have the same format. And then we have this data quality, that we will have the best added value feature. We have some extra functions in this crop-cutting service that will benefit the work with the observations. And then, of course, we'll have the feedback back to the providers that if we find something suspicious and anything else, then we can come back to the provider and ask them to look at it. And then we can get the observations back again in delayed mode from the providers. And this is a really good thing, and it's also user-driven, that the users and the providers have a dialogue with us. So, thank you, and I hope you enjoy our data.
Joanna, I think that we don't have any question for you right now. I just wanted to mention that to all the participants that you will have the possibility to explore all this in-situ data through the practical session with different exercises. So, and of course, you will be able to ask questions during these 2 weeks, two coming weeks. And Joanna and also Paz Rotland, who will be your trainer for the in-situ data, will be able to answer your questions as well. There's a question about TAC. What does TAC mean? So maybe, Joanna, you can answer this one.
Yeah, I brought it up in the beginning. It's the Thematic Assembly Center. So it's in Siemens we use this for like a group you can think of, like we are the in-situ group in the Siemens. And there are also other groups for like waves from satellites and sea ice and so on. But Thematic Assembly Center is what it stands for.
Thank you, Joanna.
Yes, the producers in the Copernicus Marine Service are divided between TAC, Thematic Assembly Center, as Joanna said, for all the observations data, and the MFC for Monitoring and Forecasting Center for all the center who provide data from models. So now.
Okay, so now we can move on to the next presentation about the sea ice products. This presentation will be given by Juha Karvonen from the Finland Meteorological Institute. Juha? Thank you. So
okay.
you
Okay.
Max. Thank you.
I have to. Okay, it's there. Okay. So my topic is the Baltic Sea Ice Production Unit, which is part of this Sea Ice TAC, which is the Sea Ice Thematic Assembly Center, as we found out in the previous. Okay, the outline is something like this. Introduction, something about products, some more details on the products, few words of the users, and validation, evaluation, and product evolution. Okay, Sea Ice TAC is also coordinated by Met Norway actually it's Bergen now, but it used to be in Oslo. But anyway, the partners are Danish Meteorological Institute, Danish Technical University, British Antarctic Survey, FMI, also Finnish Meteorological Institute, NERSC in Norway, in Bergen also, and Ifremer, France. And there are different kinds of sea ice related products also. Okay, here is where we are located at FMR. We are in the Marine Research Unit, and the automated products are produced by the Marine Research Unit in the Polar Oceanography and Sea Ice Research Group. And on the other hand, the ice chart related products, which are produced manually and then greeted and provided for CMMs, are produced by the Marine Services, which is under another unit at FMI. Here is just an example of some kind of ice winters in the Baltic. Actually, this is a little bit historical data, but on the left-hand side, there is a very severe ice winter. In the middle, there is a typical ice winter, or what typical ice winters used to be still in 1990s and in the beginning of the 20th century. But and now there is some less sea ice. Well, okay, but products, we have had two kind of basic product lines. This ice chart related products, which are numbered 011, 004, and there is sea ice concentration and average sea ice thickness products. And they are in 1 kilometer grid. And then there are these satellite-based automated products, 011 products, which are ice thickness and ice drift. And there is also a mosaic product for the ice thickness. And this ice thickness and ice thickness products are in 500-meter resolution, and this ice drift is in 800-meter resolution. And then there is also coming, actually running all the time, automated ice concentration product or sea ice fraction. It's the same thing. So it just means how much of the area is covered by sea ice. These are also near real-time products, especially those SAR-based products. The ice charts are daily products, and so the mosaics are also actually by daily. This ice thickness and this concentration is a daily product. Next one. Okay, we use a lot of Earth observation data. The most important source of information are the Sentinels, especially the Sentinel-1A and B. Then we also receive complementary SAR data from RADARSAT-2, which is a Canadian instrument, Cosmos Skymet, which is an Italian consortium of satellites, and also from TerraSAR Rex TandemX, which is a German or German instruments. The Sentinel-1 and RADARSAT-2 are operating at C-band, which means that the wavelength is about 5 centimeters, and the other instruments we use are operating at X-band with a wavelength of about 3 centimeters. And also many other data sources, Sentinel-2, Sentinel-3 microwave radiometers, for example, MSR-2, SMOS, soil moisture and ocean salinity instrument, and Cryosat-2 microwave altimeter or radar altimeter. Okay, then we also have these ice charts and automated products. These two product lines. Ice charts are made daily by the ice analyst at the ice service, and they are based. They draw polygons and assign some attributes related to the ice properties to these polygons, and then they are gridded, and these grids are delivered to CMMs. Here is an example of an ice chart. It's not a very new one. It's from the previous winter, because this winter was not very good for the sea ice, or there was so little sea ice. Then a diagram of the production volumes. The blue ones are the ice chart products, so they are daily products, and there is about 30 products each month. And then there are these automated, excuse me, automated products which depend on the amount of available SAR data. And then there are also the Sea Ice Drift product, which is dependent on the amount of SAR data also, but it's dependent on the amount of overlapping SAR pairs actually, so there are more of that data. Okay, here is the production chain. So we, in the upper part, there are these satellites which are received at different locations, and then they are received at FMI by FTP pool from Canada MDA, from KSAT in Norway, and from ESA, and also from our own Sodankylä ground station in the northern Finland. And then they are processed either at Sodankylä or in Helsinki, and then delivered to Met Norway, and from Met Norway to Copernicus. And also they also deliver to icebreakers, the Finnish and Swedish icebreakers through the IBNet service. Okay, just an example of a C-band SAR mosaic consisting of Sentinel-1 and RADARSAT-2 satellite C-band SAR data, the HH channel on the left and the HV channel on the right. This is what we use as an input for the algorithms. Okay, I already mentioned this, that the nominal resolution of this ice chart, gridded ice chart products is 1 kilometer, and they are made by human ice analysts daily, either at FMI or SMHI. We are kind of doing it so that every other week FMI is doing more making the ice charts, and every other week SMHI. And they are daily products also. Now here is an example of the ice chart products, the ice concentration on the left, white meaning 100% ice, and dark blue meaning open water. Well, actually this gray here means open water, and dark blue means very low ice concentration. And the ice thickness on the right-hand side, you can see that the ice thickness is something around 40 centimeters in these green areas and less in. But this is again last winter. Here is an example of this winter. We can see that there is not so much sea ice in the north. There is in the Gulf of Bothnia. There is some sea ice, but not so much in the Gulf of Finland. Okay, then we have these automated products which have a little bit higher resolution, 500 meters. And well, okay, they are using the C-band data at the moment. Here is an example of the ice thickness mosaic for the previous winter, 2019. You can see the evolution of the sea ice, and here is an example for this winter. This is about the maximum ice extent for the winter 2019-2020. In the beginning of March, or even the Gulf of Bothnia was not totally covered by sea ice, and not so much in the Gulf of Finland. Okay, then we also have these sea ice concentration charts, which will be in CMEMS next winter. They also have this 500 meter resolution are based on SAR data and EMSAR2 microwave radiometer data. And they already actually exist for this winter and previous winter already, so they can possibly also be included in the CMEMS data if there is interest. Okay, here is an example, some examples for the previous winter and theory for these winters, and we can see the evolution of sea ice for this winter here. Not so much sea ice. Okay, then there is this ice drift product, which is also this automated product, part of this automated product. It's based on two-dimensional cross correlation, locating two-dimensional cross correlation maximum, and then it's computed for daily for each overlapping SAR image pair, which have temporal difference less than 3 days. And then we give the U and V coordinate values of the drift in meters and also the quality index. An example here is a SAR image of, let's say, it was in the previous 21st of February 2018 and then 2 days later. This is the 21st and then the 23rd of February, and then the resulting ice drift vector field in the white areas. There, the data was the cross correlations were so small that the ice drift was not, we were not able to define the ice drift reliably, so they are left blank. But the vector field is clearly visible that the ice is moving to the southwest in most areas, and then in the fast ice areas it's not moving there in the northern part. Okay, the users who I actually users, the most important users are navigation, ships, maritime administrations, icebreakers, and other authorities connected to marine transfers. Then there are ice services, of course, modelers in Copernicus. This is the reason for using NetGDF data format actually. And there is research use, offshore and coastal activities, for example, construction of some kind of windmill parks and so on. Yeah, okay, and the NetGDF file format is also not the best format for example, for mariners, and there are some plans to include some other formats, for example, vector graphics format of the ice charts, and also possibly GeoTIFF or something like that, but it's still in progress. Okay, then there will be, of course, product upstage because there will be new instruments and so on, and also product evolution, improved algorithms, better resolutions will be included, especially after we have higher resolution instruments. And of course, we will also try to improve the accuracy and also include some new automated products. Some detailed, okay, we have this sea ice drift algorithm, a better version is under construction now, which seems to be underestimating the magnitude of the ice drift, and we hope this new algorithm will perform better. Then we have this ice thickness. Now it's working only for Sentinel-1 extra wide SWAT mode, but we also want to work with what is internet wide SWAT mode, interferometric wide SWAT mode as well, and also for expand, and also better ice thickness products using more of these available instruments. There are also radar altimeters and microwave radiometers, which are not utilized fully utilized in the current algorithm. And also there will be probably ESA will provide L-band SAR data, which is better for example, for ice thickness estimation, because L-band SAR penetrates deeper in sea ice. Okay, then there's this validation and evaluation operations. We use all the available data. There are measurements available, some measurements available for the sea ice concentration. We can use only microwave radiometer products as a reference. But we have, for sea ice thickness, we have icebreaker measurements. For the ice drift, we have some drifter GPS buoys, and then we have occasional campaigns where we make this, for example, this electromagnetic induction measurements for sea ice. And we also have these sea ice mass balance buoys, which measure the sea ice thickness at a given location. Unfortunately, this winter the sea ice was too thin, so we could not mount SIMBAs in the usual occasions. And then we provide these quarterly reports, these data quality reports, actually only for Q1 and Q2 in the Baltic, because for the rest of the year there is not so much sea ice and not so much to report. Well, okay, I guess this was what I had to say. Thank you.
So we have time for a quick question. Fabrice, yes, thank you. So it's a question by Marta. Is there any validation for the melt period and how high errors are during the melting season? So if you can answer, Yura.
The melting period, and for the ice thickness, the errors are quite similar as during the midwinter, but for ice concentration, well, it's difficult because we don't actually have good validation data for the ice concentration, because we can only compare between other ice concentration products. Our ice concentration product has much higher resolution than this typical microwave radiometer products, but it's difficult to say. And after this season, we will try to compare the ice charts and the automated products, but still it won't provide, possibly, because the ice chart, ice concentration may also be biased. There are not really, it's difficult to measure by any other way than remote sensing. So ice thickness, yes, there is validation data available, and there is the L1 errors are typically something between 5 and 10 centimeters for ice thickness, but ice concentration, I don't remember the numbers. They can be seen in the data quality reports. I think they should be available somewhere.
Okay, thank you. For all the other questions, once again, we will answer later on. So sorry if we don't have time to do it now, but we are going to move on to the next talk, which will be given by Vibeke Huus from DMI. She is going to present the Baltic Sea forecast model products. So Vibeke, it's your turn. Thank you. Vibeke, we can't hear you. Sorry, you have to open your microphone.
I think it's working better now. I thought I clicked on it. You can hear me now, I hope. Super, thanks. Good morning, everybody. And I will present the model products that we are doing for the Baltic Sea within the marine service in Copernicus. And I will do two different presentations. As I'm sure here. The first presentation will be about the forecast model product, and the next one will be about the hindcast or the multi-year products that we are doing. So the difference between those two different presentation and product types are that the model forecast products are looking forward in time, and we only have 2 years of data back in time available on the catalog, on the online catalog. You can request more data back in time if you need that. So we have 3 different forecast product. We have for the physical ocean state, we have for the wave dynamics, and we have for the marine ecosystem. And we do what you can go in and find is the latest forecast, and as I said, 2 years back in time on a rolling archive, and it's updated twice per day and with a 6 days forecast. And the purpose with this is, of course, to give you an operational product for the Baltic Sea to be used for any operational activities that you might wish to look into for the Baltic Sea. First, I will give a very short introduction to the BAL MFC, the Baltic Monitoring and Forecasting Center. We have all those acronyms in the CMEMS system. We are a consortium of 5 Baltic Sea institutes. I am from the Danish Meteorological Institute in Denmark, and we are leading this consortium. And with us, we have the Swedish Meteorological and Hydrological Institute, SMHI. We have the Finnish Meteorological Institute, FMI. We have the Federal Maritime and Hydrographic Agency in Hamburg, in Germany. And we have the Marine System Institute as part of the Technical University in Estonia, in Tallinn. All those 5 institutes has a very long tradition of doing operational oceanography activities in the Baltic Sea. And we all have national obligations for the Baltic Sea. And we also, in addition to this, we have also a very long tradition of working together during the last 20, 30 years within the Baltic Sea corporations. So when the Mercator gave us this opportunity to have a contract for providing the CMEMS model product for the Baltic Sea, we decided to join our forces and go together and work very, very close together on providing what we hope could be the best model product for the Baltic Sea. So, as I have said, we have 3 different forecast products for the physical and the biogeochemical and for the wave. And I have listed here the name of this, and you can recognize the structure of the product names from the different presentations now. And one thing, I'm not sure if Cedric actually said that you can go in and search for a product by just searching for the last numbers. So the 003 is meaning that it's a product provided by the BAL MFC. And then the product ID itself is the last numbers. So as I said, all those 3 products are updated twice per day with the latest forecast available. And it should be ready in the catalog at 10 a.m. UTC in the morning and again 10 p.m. in the evening. So I will start with introducing the physical ocean and marine ecosystem, and I will take this 2 products they are in the Siemens catalog as 2 different products, but they are produced by one simulation. It's a coupled system. I'll show that here. The model system behind our ocean and biogeochemical forecast products are coupled it is online coupled production with the ocean model called HBM. It's a original German developed 3D ocean model, and now it has been used in the Baltic Sea community for many years. It stands for Hiram Booth's model system. And then that is coupled to the biogeochemical model Ergon. This is also a German developed system from IOW in Warnemünde in Germany. We are running this system for the whole domain covering the North Sea and the Baltic Sea, even that we are only producing a product for in the Siemens catalog covering the half of the area nearly. So it covers the Baltic Sea itself, of course, and then the transition area towards the North Sea. The native resolution of the model simulation is for the North Sea a 3 nautical mile system, and for the Baltic Sea itself a 1 nautical mile resolution. And in the very narrow transition area covering the Danish Straits, it's in a half nautical mile resolution. That is simply to be able to simulate the ocean in the area correctly. The maximum number of model we have in the model setup is 122. So, as I have said, it's produced twice per day with a 6 days forecast. The atmospheric forcing data is for the first 2.5 days. We are taking the best available atmospheric forcing we can get. So the high resolution that we are running for the regional area, and for this physical and bio system, it's coming from DMI's operational production of the Harmony system that we are running for the Scandinavian system or area. So that is in a resolution of 2.5 horizontal resolution or kilometer resolution, and with hourly resolution in time. Then for the following 3.5 days in this 6 days forecast, it's produced by using the ECMWF operational model system, and that is coming for the time being in a resolution of 9 kilometers grids, and in the time we can get the data with a 3 hourly resolution. At the model's open boundary, we have an open boundary north of the North Sea, if you say between Scotland and Norway, and in the English Channel. We are having input from a tidal wave we are putting on the boundary, and then we have a search model to include searches coming from the northern Atlantic. That's important for the North Sea at least, and it's also propagating into the Baltic Sea. We can see an effect there. Then we are of course having a temperature and salinity, and we are using data from a climatology, and that is okay because the product we are providing for you is only for the Baltic Sea, and to have climatology in the North Sea, it seems to work okay. Again, for the bio model, the Ergon, we are using climatology at the open boundaries, and simply because there are no other information there. For the river runoff data, we are having real-time data from SMHI, the Swedish Met Office operational hydrological system called eHynd, and we are using that. So that is real-time data from a modeling system that goes into this. This is a very big advantage of our forecasting system, that we are having real river runoff information and not using climatology for the river runoff data. Yes. Here you can see the exact product area. We are producing the product on only 25 depth levels, and that is actually a historical reason. In the beginning, we couldn't provide, for technical bandwidth limitations, we couldn't provide all the model that we are, or all the levels we are producing in the model. And for the horizontal resolution, it's 1 nautical mile. We are producing 3 different data set. So one product is as described earlier. So one product has different data set. So we are producing an hourly instantaneously data set. We are making a daily mean data set, and we are making a monthly mean data set. And the last thing we have here is that the model itself is running on a Arakawa C grid, and the product, all the product data we are providing are provided at the grid nodes. So this is just for your information. Some detail for the product for the physical ocean. We are providing water temperature and salinity and the horizontal velocities in the 3D field. So at all the 25 vertical depths. Then we are making some 2D fields also, the mixed layer depth, the sea level and the sea ice concentration and thickness. And then we have decided that the bottom temperature and salinity might also be an interesting variable to have a quick look at. So we're also providing this as a final product field. And then I said that we're using this HBM 3D ocean model. And we have used that for many years in the Baltic Sea community. We are in a process to change to another open source ocean model system, the NEMO, as I guess a lot of you are aware of. That is the model, the ocean model that are used in most of the CMEMS model centers. So we are working on that now and shifting from the HBM to the NEMO system. But that's not released yet, and we are working on that. So for the bio product, we are having we have listed here the available parameters: the chlorophyll, nitrate, phosphate, ammonium, dissolved oxygen, and again as a quick service, we have taken the dissolved oxygen at the bottom layer from the model, and we have the SIC depth. And again, we have hourly instantaneously values, and that cover all of them except, and then we have the daily mean and the monthly mean. And that's daily mean and monthly mean has all the available parameters except the SIC depth, because it doesn't make any sense to have a mean of the SIC depth. And we updated this bio, the Ergon model, by the last catalog upgrade of the CMEM system in April, so 2 months ago. And there we included a carbon cycle also to have the accumulated net primary production as a data or a variable, and the surface of the atmospheric CO2 pressure and the pH. So coming back to the WAV product. This is produced by the WAV, open source WAV model, also developed original by Germany. So we have a lot of German models in our systems. And it's running on the same product area, and it's exactly the same grid as for the physical and the bio model simulation. For the available parameters, we have wave heights, wave periods, directions, and the Stokes drift. For the wind waves, the swell, and the total wave field. And this should be the same parameters available for all CMEMS model area. And again, it's a 6 days forecast, updated twice per day. So exactly the same production cycle as for the ocean and bio. And the same atmospheric forcing in principle. It's the harmony system for the first 2.5 days in 2.5 kilometer resolution and with hourly time resolution. But for this time, we are using FMIs, so the Finnish Meteorological Institute operational system. And again, for the following days, it's the ECMWF data. So the same structure and the same data set in principle. It's the harmony model, but it's from the ocean, it's the DMI, and for the wave, it's the FMI. So there might be slight changes in the atmospheric forcing, and we are working on harmonizing that. But in principle, it's coming from the same weather model. And again, we have an open boundary in the wave model setup, and the wave spectra is coming from ECMWF deterministic wave forecast. And we are reading in the surface currents from the physical simulations we are doing into the wave simulation. And the ice concentration are from the ice charts to block out area with ice, so there are no wave calculations with the ice. This is just a slide, but Cedric have introduced this very nicely, that for each product, so when you are interested in a product, go in and have a look at the product user manual and the quality information document. In the product user manual, you can go in and see what are the different variables called, and so that you can download the parameters that you are interested in. And the quality information document, what we call QIT, to make it easier to say, you can go in and find the quality of a 2-year period before we went operational. So it's a static period that we are validating. We are also having a lot of information on the BOOS website, but I could maybe provide some information more on this. We are supposed, or the contract that we have with Mercator is that our products are required to be state of the art, and we are of course hoping that we are providing that. We are doing our best to do that. And one thing is that we get money here in Siemens to do a continuous model development and product development. On average, we will upgrade our forecast system, so the system behind the products on an annual basis. So we have about 1 annual upgrade of the system to be sure that we are keeping focused on having the best model system and the setup and input data. So just a little of what can you actually use a forecast product for. Maybe you are aware of all this. You can use it as a boundary condition for more local models. I saw earlier that there were some questions about the coastal modeling system. You can use it, of course, as safety at sea, sea level forecast, flooding and low sea level, and drift forecast for different purposes. Yeah, I think I'll skip the rest. So thank you very much for your attention for this. And Mathilde, shall I just continue, or you can decide if we should take any questions?
Yes, maybe. Thank you, Vibeke. Maybe we have yes, 2 short questions before continuing. So first, does all the Baltic Sea data cover the Gdansk Bay area?
Yes, I would say so. If it has an open connection to the Baltic Sea, but I'm pretty sure that the Gdansk Bay has that. But as we can go in and have a look.
Okay, and the other one is sedum and suspended matter considered in SECI-DEPS modeling?
And here I have to say that I need to contact my bio experts for answering that.
Okay, fine. Well, that's the idea, that during 2 weeks we will be able to answer the questions, so no problem. And so we can continue to your second talk on the hindcast products.
Yes. Yeah. Thank you very much. And now it will be about the multi-year product. So this is the same slide as before, but now we are at the multi-year product presentations. I want to say one thing about why we're splitting this between a forecast product and multi-year, and that covers all the different model centers in CMAPS. That the goal with the multi-year product is that it's the whole production is not touched, or the whole system behind the final product is not touched for the whole period. So all of us are starting for all the global and the regional area. We are starting in at least back in 93, and then we are running up to as close as possible to present. And the idea is that this is done by a homogeneous system. So the model code is the same, the model setup is the same, and hopefully all the forcing data are coming from the same sources with the same quality. So what you see of differences are caused by the simulation or the nature itself in the model system. And that is a little bit different from the forecasting system. So it is to have a homogeneous production system behind this. Yes, I will skip this as I went through this. And again, we have 3 different reanalysis or multi-year product in the catalog, covering the same: the physical ocean, the biogeochemical ocean, and the WAV. And the WAV hindcast is relatively new in Siemens. I think all the regions have a WAV reanalysis, as I remember it now. Ours was just released here in the April, or the end of March, the last day in March. I think we upgraded the catalog. So this is a brand new product from our site. So if we're looking at the physical and the bio reanalysis product, and again, I will take that as one system because it's run as one system. But this is another model code system as compared to our forecasting system for the time being. So the forecast and our hindcast products are not produced by the same system for the time being, and we are again working on harmonizing this. So what we are producing here for the reanalysis product is a system based on NEMO 3.6, and online coupled with the Swedish developed biogeochemical model called SCOBY. It's again running for the North Sea and Baltic Sea area, and this is the typical model domain we are running Baltic Sea models in, to simply cover all the dynamics coming from the North Sea. It's the native resolution of this model simulation is 2 nautical miles, and it has a maximum number of vertical depths of 56. And this is exactly the same as you can find in the product. So here you are having the native model grid points. And I have said here that the update frequency is yearly, approximately yearly, where we are extending the system. So, but running with hopefully the same system as produced back from 93. So there are no changes in the system when we're updating this. So right now we have data available in the catalog back from 93 to 18. And as Cedric very kindly already shown, that we will, for the next upgrade of the catalog, we will upgrade with the next half year. So the first half year of 2019 is already produced, and it's ready to go into the catalog. And then we have put the atmospheric forcing data here, and you can actually see it's not possible for us here to only have one forcing of atmospheric data. We use the data from a product called Euro4M, and that covered 93 to 2011. Then this product stopped and there were no more data. So SMHI that has made this product used the reanalysis data for the last 7 years from ERA reanalysis. So we are simply not able to, or we didn't manage to find atmospheric forcing data that was homogeneous over the whole period. But we took the best we could find. And again, open boundary, we put the same parameters as for this forecast, a search model and climatology. And again, we are having runoff data. We are in the lucky situation that SMHI has this hydrological system running, and we use data from that one. We have data assimilation in this reanalysis product, and we are assimilating sea surface temperature from satellite. And we are also assimilating profile data of temperature and salinity from in-situ measurements. And also for the biomodel, we are simulating profiles of nitrate, phosphate, ammonium, and oxygen. And here you can see what's exactly available in this product. I think I have covered the most. There's the daily and monthly data set from the physical, the water temperature, salinity, and the horizontal velocities, mixed layer depth, and bottom temperature and salinity. And in the hourly data set, we decided that could be interesting to have for this long period, the sea level, and also the sea ice. And for the bio from the SCOPY model system, we have daily and monthly mean data set for nitrate, phosphate, ammonium, chlorophyll, dissolved oxygen, and also at the bottom. For the WAV reanalysis, as I said, it was just released, so we spent last year to produce this, and that is produced by FMI in Finland. It's based on the WAM 462, exactly the same as we are running in the forecast system, and it covers the same time period, so back from 93. And it's run in 1 nautical mile, and that is also exactly the same as our forecast product. The atmospheric forcing, there was a new data set available because we just did this last year, where the physical and bio that I have just went through was done about 3 years ago. And then the ERA 5 produced at ECMWF atmospheric forcing was not available. It has just been released the last year or so. I guess you are aware of this. And for the forcing for the ice, we are having data from SMHIs. There are historical ice charts. And at the open boundary, it's the wave spectra from ECMWF, exactly as in the forecasting system. And again, this will also be extended with an update frequency of about yearly updates. Again, it's exactly the same parameters as we are producing for the forecast. So it's for the total wave field, and it's for the wind wave and the swell as well. And it's significant wave heights, it's wave periods, and it's direction, and it's a Stokes drift. Yeah, and I don't want to repeat this third time. You can always go in and find more information. Exactly the same as with the forecast product, that we are supposed to deliver state of the art, and we are doing that, but by having a continuous development and using our network to ensure that we are having the best model system, running the best model system. And we have suggested that we have had a 3-year contract with Mercator to provide the Siemens data, that we once per contract, so once per every third year, we want to produce a new reanalysis product to be sure that we get more data to be assimilated and have the best forcing data. And then there are something that are already old on this slide, even that it's only a couple of weeks. We planned some extension, and the first one is that we will have a temporal extension for half a year. That will be available from July this year in the catalog. Then there's something about interim, where we had to run as close to present time as possible. That has been postponed by Mercator because we are not really ready to handle that in the system right now. So for the time being, we are extending our hindcast or multi-year product with approximately twice per year with half a year extension every time. So the physical and bio will be extended in July, and the WAV will be extended with a full year in December, in the next upgrade in the catalog from December this year. So just to mention, what can you use this multi-year product? My colleague Friedrich Lagemann will show that in a few minutes. You can use it for estimating the climate and see trends for this period where we have produced it. But you can also use it for a little bit more operational activities, as if you want to put a cable on the seafloor, you can go in and see what has been the maximum or the minimum temperature for this 28 years that we have now, 28 years that we have now. So you can use it for investigating different parameters. And I think I will leave this. Just say thank you for your attention for this also. And I hope it was clear with the splitting of the forecast and the hindcast products.
Yes, thank you, Vibeke. I think we have one question about the difference between these two products, actually. So maybe Fabrice will put it online. Or do it? Oh, okay, thank you. So how consistent are the forecast products versus the reanalysis products? And what are the typical differences that we may expect between these two products?
That's a very big question, but they are not as consistent as they could be, because we are running to a different modeling system, and it's forced by different forcing data. Potentially, we could answer that later, I think. And maybe my colleague will also Friedrich can also say something about this, because we have tried to look at them for overlapping build. It's coming from different modeling system, and there will of course be something that are not consistent between such two different simulations. I don't know if that, maybe we can answer more with a better answer later on.
Okay, thank you. Thank you very much, Vibeke. So we can move on to the last talk of this webinar by Friedrich Lagemann from the Tallinn University of Technology. And Friedrich will present us the Baltic monitoring ocean monitoring indicators. Sorry, and maybe Friedrich, if you want to say a word before on the question that was asked previously, of course you're very welcome. Thank you.
Yes, hello. My name is Friedrich Lagemann. Yes, about this question, they at some places they are quite different, and as Vibeke said, it's due to the different modeling systems. But we are working on this direction to make these differences smaller. Yes, that's one point you have to consider. But now to my presentation. So I talk about the Baltic Sea monitoring indicators, which are one of three categories of the main products that CMEMS provides. Yes. So as Fabrice already mentioned, there are also ocean monitoring indicators and ocean state reports together with the data in CMEMS product portfolio. And so far the talks have been mainly about the data, but now I talk you a bit about ocean monitoring indicators and also a few words about ocean state report. So about the ocean state report, ocean state report is a set of peer-reviewed papers which aim to give overview of the state of the European seas. It's mostly designed to the scientific community, but the executive summary also targets the policymakers and decision makers. So it's good to read the material. So the OSR production started about 5 years ago, and first ocean state report was published in 2016. And starting from that, we have tried to publish a new report every year. Well, sometimes it takes more time, but yeah, we aim to have a yearly update of the ocean state report. So now there are 3 issues already published, and the 4th one is under review. Should be published soon, and the 5th one is already in progress. So about the Baltic MFC contributions to the ocean state report. For the ocean state report 3, we have 5 contributions. That means basically 5 sections in ocean state report number 3. These are, as you can see from the slide, it's about phytoplankton blooms, then about cod reproductive volume, and then about sea level, temperature, and wave extreme percentiles, and then one section about sea ice thickness, and then one describing the storm surge extremes in the January 2017 storm. And for the ocean state report number 4, this one is not yet published, but we will have 2 sections there. It's one is about sea ice coverage, and one section, other section is about surface warming in the Baltic Sea in extreme hot summer 2018. And you can also notice from this slide that the ocean state report is also, so to say, incubator for the ocean monitoring indicators. So all the ocean monitoring indicators must first be published in Ocean State Report. If we move on to the ocean monitoring indicators and you want to know more information for some monitoring indicator, then you can always find a section in Ocean State Report which gives a comprehensive overview of each OMI. And now let's move to the ocean monitoring indicators. Basically, these are, so to say, easy to use, simple products. Very well, I think most perhaps easiest example is the global sea level rise indicator, which is simple time series of sea level rise. But well, that's good to well, easy to understand what these indicators mean or try to be. Basically, they show trends and anomalies of key variables. They cover the data from 1963 to nowadays. Well, not yet to present time, but I think the latest one ends in 2018 at the moment, and they are updated yearly at the moment. And as Cedric also already showed, they can be found on CMEM's website and data portal. And now I have gathered here the OMIs that show something about the Baltic Sea. Mostly the OMIs are produced by Baltic MFC, but there are also other OMIs which describe Baltic Sea and are produced by other production units of the CMEMS. So basically, what we produce in Baltic MFC is the subsurface salinity and temperature anomaly, and also the trends of the salinity and temperature. Then there are two OMIs for the ice volume and the ice extent, and then for describing the inflows of the Baltic Sea, there are evolution of salinity, temperature, and oxygen, and also the bottom salinity time series. And finally, there is card reproductive volume OMI. And the other OMIs are more for the satellite products derived. They are chlorophyll A time series and trends and anomalies, and then mean sea level trends, temperature anomalies, and so on. But I will focus here on the OMIs produced by Baltic MFC. So first, about the subsurface temperature and anomaly OMIs. On the left, you can see the anomaly maps, which is time depth map, shows the anomalies over the last 25 years, and the profile next to the anomaly map shows the most recent year that is included in this OMI. So then you can see the details of how this anomaly is in last year. These anomalies are calculated from the reference period, which is defined to be from 93 to 2016. And this is simply defined in Siemens OMI framework to have this reference period. And basically, it's horizontally averaged over the Baltic Sea domain, and it's based on reanalysis model data. On the right side, you can see the trend OMIs. It's similarly to anomaly OMIs. It's calculated from horizontally averaged temperature and salinity from the reanalysis product, and it shows the trend profile for how the temperature and salinity is changing over the depth in the Baltic Sea. And then next we have the sea ice OMIs. On the left side there is sea ice extent OMI, and the right side shows the sea ice volume OMI. Basically, these are the time series of the sea ice extent and volume, and the upper graph shows more specifically the latest year, which is included in this OMI. So each time the OMI is updated, this upper panel changes and shows the most recent year. So one can easily say if the recent year was normal or below normal, or well, not normal but below average, let's say. And then about the inflows, we have also two OMIs. One is on the left side is time depth evolution of salinity, temperature, and oxygen. These are based on in-situ data. Actually, it's not the model data here, and it shows simply the time depth maps at the Gotland Basin. And then on the right side we have the bottom salinity time series extracted from the reanalysis model, and show the bottom salinity at Bornholm Basin and Arkona Basin. So basically, with these four figures, we can say what is the inflow conditions of the Baltic Sea, and estimate the health state of the Baltic Sea, so to say. And finally, we have this Baltic Sea Cadre product volume OMI. This one is not yet published on the catalog, but it's on its way. So hopefully it will be during the summer. But it shows the water volume of the Baltic Sea, which is suitable for the cod reproduction. Basically, it's a volume of water which has salinity over 11 PSU and oxygen over 2 milliliters per liter, and temperature over 1.5 degrees Celsius. So this, this OMI basically describes how good is the Baltic Sea state for the cod reproduction. Now, similarly to all products that CMEMS provides, the OMIs also have the user manual and quality information documents, which are all available in a similar manner that all the products have. So if you have any further technical question, you hopefully can find more information from these documents. And that's all. Thank you for your attention.
Thank you very much, Predik. Just check quickly if we have. No, so we don't have any question for you. That was very clear. Thank you. And now I leave the floor to Fabrice, who will say a few words about what's coming next. So, Fabrice.
Yes, thank you, Mathilde. So the next round for this workshop will be the 15 days coming next. You will receive soon an email to access the Jupyter Hub platform. On this platform, you will access to 19 exercises in Python, and you will find the video related to this Jupyter Notebook on the YouTube channel of the Copernicus Marine Service. And during the round 3, you will receive at the end of this round 2 a new invitation to the debriefing session, the round 3 of this workshop. So the debriefing session is planned for the 8th of June, 8th, 9th, and 10th of June, with a different session regarding the different type of products. Okay, so I hope all is clear. Don't hesitate to ask us if you have any question. I would just put this slide, and thanks again with Mathilde. Big thanks to all the experts, the speakers. Sorry for Predik and Virginie. I forgot the Taltech and IC icon. Okay, I repaired my mistake. Sorry for that. So thank you for all the presenters. And I think, Mathilde, we have a quick survey before to close this.
Yes, so thank you very much to all the speakers, but also to all the attendants, to all the attendees. We were more than 140 people listening to this webinar, so that's amazing. And we would be very happy to have your feedback on this webinar. So if you can answer this survey, this online survey, you can directly click on the screen and answer your questions. Thank you very much. And I hope that we will see you for the second webinar session for the debriefing about the practical exercises.
Thank you. Thank you all. Thank you, Mathilde.